Well, thanks. Thank you for being here. Thank you, Arthur, for a nice introduction. It's a pleasure to be here. Nowadays, I am acting as a director of the National Laboratory of Nanotechnology in Brazil. And as Arthur mentioned, I'm also a full professor of physics nearby. The University of Campinas is nearby this National Center of Nanotechnology. And I will try to show to you a little bit of what we do in my group about nanomagnetism. But before starting, I will try to give an outline of what I will present. And of course, I didn't know exactly the audience, how much about magnetism or about these basic ideas of magnetism the audience would have. So I must apologize from the beginning. I tried to give a balanced seminar, so very introductory. So to the ones that already know something, maybe it's a little bit too basic. But I try to mix a little bit of science with applications, so it will be a little bit more interesting for the ones that are not in the field. So I will try to show, and basically my group that we do is working on granular systems of nanocrystalline systems, which are of this kind. So we have a matrix, whatever it is, could be a solid or could be a liquid or a metallic or an insulator or whatever, and some granular system, nanocrystalline system. So just to mention or show one example, this is a typical sample that we work with. It's a cobalt nanoparticle on a silica matrix, and this is the kind of system that we are dealing with. But before starting showing that, just to show you what we are located in, this is the Brazilian Center of Nanotechnology. This is not comparable to this building, so it's smaller than this one. This is the Nanotechnology Laboratory, National Lab. But we are in a campus together with the synchrotron light source. Nowadays, the synchrotron is this one. But they are building, as you can see, a new synchrotron source here. It's the Sirius. It will be, it's planned to be built in, probably next year will be finished, and starting in 2019 to have the light. So they are really building a completely new fourth-generation synchrotron light source. Also, we have a national center here of bioethanol and renewable energy, and here biotech national lab. So we have a complex of 4 national labs working together in materials and energy. So it's called Centro Nacional de Pesquisa em Energia e Materiais. So it's National Center for Research, Energy, and Materials. So this is the complex that we are talking about. And the University of Campinas is just about 1 kilometer far from this complex. So it's rather close to the university. And regarding our center, the National Lab of Nanotech, it's rather new. It's about 4 or 5 years old. It started with electron microscopy, some probe microscopies, and microfabrication. And now it's starting to grow. So we have metal processing, nanostructured materials, sensors and devices, cryomicroscopy we are starting now, and there's a new group of nanotoxicology. Whenever I tell you about these groups, they are really starting groups. We have 2 or 3 people. Generally, we have about 20 staff members, only that. In total, we have 93 people working, but we are counting all the students, all the stages, and all people that work together in this lab. So this is a rather interesting and new lab, but there are very interesting and good opportunities and facilities. And being a national lab, we work, it's an open facility. So when everyone, not only from Brazil, but from all over the world can apply to make any project, any measurement there. So you go online, there is a form, and then you put your project and you can apply, and it's different from most of the places all over the world. It's completely for free for the users, academic users. If you are from a company, you have to pay, but if you are an academic user, it's for free. And then you have all the open facilities. We have the clean room, we have the microscopes, we have all kind of facilities which are open for the users. We have, of course, some in-house research, a lot of projects with companies, and of course also education and outreach program to train people to work with microscopies and nanotechnology and so on. So this is a rather good facility, at least from Latin America, and I use the opportunity already to invite you all to visit us whenever you can. Well, I will start with magnetic materials. This is the main motivation. So this is Dick Tracy, a very well-known character in cartoon world. He already mentioned in 1935, the nation that controls magnetism will control the universe. Do you need any motivation greater than that one? No, so it's you can see in the world of cartoons, at least, this already happens. So you see now the villain of X-Men, for example, Magneto, it's the control of magnetic fields makes him extremely powerful. But indeed, we were even talking in the lunchtime that we are so much dependent on magnetic systems that we don't realize. So even if you don't use a computer, of course, you need to have your data, everything recorded or saved in some place. And we have this extreme capacity of storing data in this machine, which is a piece of technology which is fantastic, by the way, and we don't realize that, which is the hard disk. And well, there's a lot of technology involved here. Of course, all the tribology, all the friction problems, all the mechanical structure that you can now work, even if everything is balancing and everything is moving, the system keep working, no problems, and you can have an idea. From here you have the disk, and here you have the head, and this would be a hair, a piece of hair. So this is 15 nanometers distance without touching, and this keeps in this way even moving in thousands of rotations per second, and this works very, very well. But I will focus on the other part, which is the magnetic component of these disks, which are extremely interesting. The idea of magnetic recording is not at all new. By the way, it was discovered or thought about in 1898 by a German guy called Poulsen, and he made this very interesting technology design. So he put a steel wire, a telephone, which is a recording magnet, essentially an electromagnet. He spoke here, there's a battery here, and then a recording, by moving this carriage here down, he managed to record few seconds of his voice. After he made this recording, he just changed the polarity, and the microphone turned out to become a speaker, and then you just move this carriage down, and then it reproduced exactly the way they recorded, the voice he recorded. This was the first magnetic recording of the world. And of course, it developed a lot in the last 100 and 120 years. And the initial hard disks were essentially the same, with the same concept of the same idea. You have a disk, and the disk has a magnetic medium, and the magnetic medium have regions which are with some magnetization in one direction on the other direction. One direction would be the 1, and the other direction would be 0. Well, you have zeros and ones, and then you have a head, which is, at the beginning, it was essentially an electromagnetic device just by induction. You have a magnetic induction here, and you have a signal, and you can say if it's 1 or 0, and you can record. So the older ones here had the opportunity to have a magnetic, had seen or saw a magnetic tape working. Nowadays it's a little bit old-fashioned, but essentially the concept and the idea is the same. And of course, the challenge for the industry was to keep things moving down in size, so miniaturizing things, but at the same time, exploring more and more, having more and more space for recording, data. So nowadays the cameras have any picture have 10, one can be megapixels or 12 megapixels or whatever. So you need more and more information recorded and in a smaller space. So the challenge for the industry was to develop magnetic bits, which are these regions, smaller and smaller year after year. And this indeed happened. Just to mention, this is a rather old figure from IBM. You can see here, this is 1990. This was the size of a bit in 1990. This is commercial bits. So you see here, this is the region, the magnetic region when you store a 1 or a 0 in a magnetic way. And this was 0.6 micrometers times 12 micrometers long. And just after 10 years, essentially 12 years, this was reduced to 30 nanometers to 250 nanometers long. So this was a reduction of a bit size in the window of about 12 years. This is in the commercial hard disks. This is also for the ones that are older here. I remember the times you bought my first hard disk was 10 megabytes. The next year it was 20. The next year it was 40. Year after year, your hard drive became outdated because you had doubled the capacity. And in fact, it happened. And from 2000, 2002, you see here that in this industry of magnetic recording, the nanotechnology was already a reality back in the beginning of the 2000, because you had to control the bit size of about 30 nanometers width. And this, you can see this amazing trend of the hard disk industry among the years. So this was the first hard disk drive in '56. And notice here that this is a logarithmic scale. So you see some inflections here. I won't go into the detail, but this was about 90 million times increase on the capacity of a hard drive. My question or my problem or our problem, the industry problem, is that they can't keep growing in this rate anymore because there is a physical problem of a physical limit. Well, this is just to show you the price is also going down very, very quickly. And this is even the pace of change is even quicker than the predicted Moore's law for the semiconductor industry. So just to show you that we have a limit. We cannot, let me show you here, keep growing in this direction because there is a saturation here. We have a limit, we have a problem, which is a physical problem. We have the so-called superparamagnetic limit of these bits. I will try to explain a little bit more about what we mean by superparamagnetic limit. Whenever you have a magnetic region, you have a magnetic moment, and this magnetic moment points toward one direction, as I explained, 0, or the other direction, which is 1. Both directions are, let's say, a minimum in this energy landscape here. So you have a minimum here and a minimum there. And in order to go from one to another, of course, you can go by applying a magnetic field that makes this barrier change, and then you can change the position. But there is an energy barrier here, which is proportional to this entity, which is a density of energy called the anisotropy of the material. It depends on the material's properties. It depends on the shape. It depends on a series of things. But there is a quantity here depending on the material's property. And of course, this is a density of energy, and then you have a volume. So you can see that if you reduce the volume, you reduce here this barrier, and you reach a point with, where when you reduce this barrier, there is a point where the thermal energy, the usual thermal energy becomes of the same magnitude as this barrier. And then if you record a zero, just by thermal fluctuations, thermal noise, you can jump to the other side. So you lose, essentially what happens is that you lose your information, what's not what you want. So the problem is that already in the 2005, the industry, magnetic recording industry, already reached this superparamagnetic limit. The spins or the bits, magnetic bits, were so small that they were not stable from the point of view of magnetism anymore. So they work. I won't go into the details. You can essentially model this problem. Although the magnetic system or the magnetic materials are essentially quantum in nature, because the magnetic interaction is quantum, is quantic, you can treat the system as a classical vector if you consider all the spins in the system coherently oriented and coherently rotating. So they are rigidly aligned, and you can consider this as a huge magnetic moment which rotates freely. So you can make a very complete and rather correct classical approximation, and you can have this super spin rotating freely. And this is what's called superparamagnetic regime. So you have one particle or one region of a magnetic material which has an isotropy, so it prefers a specific direction for the magnetization to lie, and then you can jump from one to another with this energy landscape, as I mentioned before. So you can have this kind of picture. You can go from 0 to 1, and then you can make a rather common statistical treatment to solve this problem. So this is an Arrhenius frequency jump. You can calculate your relaxation time. You can make all the straightforward calculations that you probably, the ones that have seen here, at least from physics, basic statistical physics. These are conventional problems that you can solve. And then you can easily calculate the magnetization as a function of time. I won't go into the detail, but just to mention that it's in the nanoscopic regime, this is extremely sensitive to the size. Just to mention one example, a particle of cobalt of 68 angstrom, around 7 nanometers, you can have a volume. This is a spherical particle and so on. You can calculate the relaxation times to be 30 milliseconds, around 30 milliseconds. If you go to this particle to 80 angstroms, just 1 nanometer larger, this relaxation time goes to 300 years. So this is, extremely sensitive to the size of the particles. And then you can define what is called in this field the blocking temperature. And this is quite different from anything that you probably seen in different areas, because you have in this process to define what is superparamagnetic or not. It depends on your measuring technique. There is a measuring time which is fundamental to understand the problem. If you wait long enough, if you have a nanoparticle, let me come back here a little bit. If you have a nanoparticle which is big enough, you have a jump frequency, and eventually this particle will try, stay there for years, and then eventually can jump to the other direction. There is a probability, which is not zero, that this will happen. It's extremely small, but it can happen. So even huge nanoparticles, let's say, like just one extreme example will be our planet, the planet Earth, that eventually the magnetic moment of the planet jumps from one direction to the other. You know that it jumped, what is North Pole today, it was already South Pole, and it changed several times over thousands and thousands of years. And if you wait long enough, any magnetic nanoparticle is considered to be superparamagnetic. Of course, if you're not waiting long enough, if you make a typical magnetic measurement in a squid or a VSM or whatever, you use about 1 minute of measurement. So everything that has a relaxation time smaller than the measuring time, it's considered to be superparamagnetic, and the others are considered to be blocked. Just a definition which is a little bit strange. It depends, extremely depends on the measuring time. And so you can go, I won't go into the detail, otherwise I won't have time. So usually in standard magnetic measurements, we consider 100 seconds. And if you make most Bauer experiments, for example, you have 10 to the minus 8 seconds and so on. You can change your window where you analyze the system. And then you can calculate the blocking temperature where this happens. So the blocking temperature is the temperature where the system can go from superparamagnetic to blocking temperature and so on. So I will skip a little bit of this physics or more technical part. And you can then, using this very simple approach, you can calculate all your experimental, or you can model very easily, really very easily, your experimental curves, your experimental data. So you have a distribution of particle sizes, and you can calculate the remanence and the temperature dependence of remanence, or you can calculate the susceptibility, and whatever you need for the system, you can very easily calculate and take for the system. Of course, if you have the distribution of particle size and you have all the structural information available. So I won't go into the details to these things. So this was just to mention that ideally what you need is to have a nanoparticle or a magnetic system, just to come back to the problem of the magnetic recording industry, is to have a magnetic media or a magnetic bit which would have a strong stability among time. So there are many approaches that were tried. The first one was to increase the anisotropy of the system. Why not use, for example, hard magnets to make a hard disk? So it will become extremely difficult to change or to make the magnetic moment to change direction. The problem is that it became so strong and so hard that not even the field is able to change this magnetic moment. And then you can record, you can make a recording of any information, but you cannot write over it. So you keep an information forever, and you cannot change this direction. So the important thing on magnetic recording is not only to record the information, but to keep this information, and whenever it's necessary, to change the information as well. So the problem with hard magnetic materials is to write again in some system. So they tried different exchange-coupled media. They changed to perpendicular recording, pattern media. They tried everything. And some of these technologies came down. So one idea that went from Hitachi, for example, they tried to make a hybrid system with a magnetic system with a laser in order to hit locally in order to make this magnetic system to change. But it's, of course, this gives more and more complexity to the hard disk, and it didn't work out. Another idea is to make a pattern magnetic media in order to record one single bit in each of these nanostructured materials. So this is something that is feasible to do. The problem is now how to read this information in a very quick way. So there are many ideas you can see here. This is very well known and possible to do. This is a magnetic force microscopy image. You can see here zeros and ones. You can record, and of course, but it takes hours to save or to read the information afterwards. And you know that you don't want hours to read your hard disk. So this is a challenge. So there are many alternatives, nanowires. They are trying everything here in this field. The problem is that so far, no one yet found a solution, which is the next step. So maybe the most promising idea is to change completely the idea of the magnetic recording. So they are trying to make magnetic nanowires, and they are now trying to change the magnetic recording industry in order to have regions. You can move magnetic domains, and then you make the recording on this information. But this is still under development. This is a completely open problem yet for the industry. It's a billionaire industry. No one knows which direction it will move to. So there's, of course, also the competition from the semiconductor sector. So there's still, nobody knows where this will end up. Let me show a little bit more of, I will come back to applications at the end, but let me show you a little bit of basic problems that we have in this kind of system. So we have yet not only extremely important technological challenges, but we have also some basic challenges that we would like to understand a little bit more. So I work, as I mentioned, I work with this kind of systems, are granular systems, and in this example, you have already an idea that this is a very interesting playground to work around. So this is simply a sputtered sample. You can have, just by changing the composition of cobalt in a silicon oxide matrix, you can have different regimes. So you can have a conducting system, you can have an insulator with a superparamagnetic system, and you can have this the transition from metal insulator transition, and you have a lot of interesting effects here in this region that we don't understand very well yet. So just to show you one interesting example, this kind of materials, these ones are produced by melt spinning. These materials are soft magnetic materials. They are nanocrystals of irons in an amorphous matrix. And these materials are among the softest materials that we have. So they are very good for transformers and any soft magnetic materials application. Sensors as well. So all kind of accelerator sensors, magnetic impedance sensors, a lot of sensors that you can work with this kind of soft magnetic materials. And just by changing 7% of these composition, you change the zirconium by neodymium, you change this material completely by 7 orders of magnitudes in coercivity. So this is extremely hard magnetic materials, and all of this happens because of effect of a nanostructure. So the coupling and decoupling within the nanostructured materials. Another interesting example is this kind of material, just to show you some interesting examples. Whenever you change your matrix and your nanocrystal, you can change completely these studies that you can make. So this is cobalt nanoparticles in a metallic matrix. This is copper. This indeed was the first system that I started studying. And in this case, whenever you apply a magnetic field in this kind of systems, you measure the conductivity or the resistivity of the system, you have a huge magnetoresistance effect. So the resistance of this system without field is completely different than the resistance of this system whenever you apply a magnetic field. So this is a well-known phenomenon already. So this was the Nobel Prize of Physics in 2007. This is the the discovery of giant magnetoresistance, so by Albert Firth and Peter Grunberg. And these are these guys here. And in fact, exactly the same, this kind of behavior you have in this kind of granular system. So you can, I won't go into the detail, but you can study a very, very interesting physics using granular nanostructured magnetic materials. You can study here, for example, the dynamics of spins and so on in this kind of systems. Very similar to the previous one, we have cobalt, and we have here, as I mentioned before, silicon oxide. With the only difference here is that the other one, the matrix is metallic, and in this case, we have an insulator, and then we have a very interesting system. In this case, we can have a phenomenon which is completely open, yet nobody understands what is happening. Just in the metal transition, whenever you start populating the cobalt concentration here, and you go through this transition from insulating to conducting material, you have a huge Hall effect, which is called the giant Hall effect, just happening in the metal insulator transition whenever you change the composition. And up to now, there is no theory about this effect yet. So this is something that is completely open in the community, in the magnetic data. And you can have a very interesting phenomenon here related to interactions. So I mentioned a little bit before of what happens whenever you have a system of magnetic moments which are completely separated to each other. But of course, there is a problem, or there is an interesting thing, that this is in fact exactly what I study. Each single element here is magnetic. So you have a cobalt, another cobalt, another cobalt. Each magnetic element is a sort of tiny magnet. So we have here this, even though we have an insulating matrix, they interact to each other through dipolar interactions. So it's an extremely complex system which they have dipolar interactions among each other. So this is the kind of system that we don't understand very well yet. And you can have a lot of interesting, from the basics physics point of view, you can have interacting superparamagnetic regime, you can have collective blocking, you can have correlated superspin glass, and you can have a lot of interesting phenomena going on in this place. So you can have dipolar exchange, super exchange. So from the point of view of basic interaction in basic quantum physics, you have a lot of interesting problems. I will try to skip a little bit of this, but essentially what we do is try to study. It's a little bit too much for a 1-hour seminar, so I will apologize, but I will skip it. If anyone has a specific interest on that, I can come back afterwards. But we exactly do try to study the effect, which is the effect of dipolar interactions on the overall magnetic properties of this kind of system. So we study a slight change from, for example, the appearance of a slight hysteresis here in a fully superparamagnetic system, and try to model that and try to understand how it works and so on. So I won't go into the detail of these systems, but I will try to show you the line of research that we are doing. So specifically, what we realized is that we needed, in order to understand the effect of interactions on these systems, we needed better samples. As usual, probably here, everyone who is working in material science realized very easily that the best thing to have is a good sample. So this is fundamental from any point of view. So we started to develop our own samples from basic chemical structures. So we have now chemical methods. So this is a well-known methods, and we have some ligands here in order to avoid the samples to connect to each other. As you know, they are magnets, and if you don't have any kind of surface, they will just keep together into a big one. So we have these very good samples now. We can study them in the synchrotron, as I showed before, by Sachs. We can have the microscopy here, and we can compare, and we can have a rather good picture of the structure. And then you can compare, and you can change the concentration by, for example, by diluting them in paraffin. And so you have the very same sample, and just what you change is the concentration. So it's the same batch of samples, and you make different concentrations, and you can study, for example, the magnetization as a function of temperature, and you can see here clearly the blocking temperature going to higher temperatures. So it means that the dipolar interactions are playing a very strong role on the complex, magnetization of the system as a whole.
What's the size of the moment on one particle?
Of the one particle is typically 3,000 Bohr's magneton. So it's about a few nanometers, from 3 to 5 or 6 nanometers of cobalt, for example. So it's a typical size of the samples. But of course, this is an ideal system, an ideal problem. And also, as you probably already know, whenever you start working on a problem, a more complex problem appears. So it's always like that. So we started trying to make very good samples and very controllable and so on. And suddenly, we managed to make, we wanted to go from cobalt, and then we made a nickel sample, and apparently we were able to make very nice and very stable amorphous nickel nanoparticles. And this was done, and the nanoparticles, whenever you measure now the magnetic properties, they have a completely strange magnetic behavior. We still don't understand very well. We try to model and so on. But whenever you make a step, there is a more complexity in the system, and there is something going on that keeps making at least our jobs more interesting. This is very, very interesting indeed. So let me just show you what we are now able to control a little bit more by the chemical methods that we are using. So we just managed to very much control the size and the shapes of the nanoparticles now. And the last one that we made was this very interesting sample, which is, we call it nanobrick. It's a rectangular sample of iron oxide, which has a silver nanoparticle in the middle. This was discovered just by chance. We don't know yet any applications yet, but indeed, it's a really, really interesting and reproducible sample that we are now able to make. And this opens a completely new way and new possibilities and applications. I will try to show you one application that we are thinking why we managed to make this sample. I'm going now back to some applications, and the idea is that you can not only have these nanoparticles on a solid matrix, you can have a liquid matrix. And whenever you have a liquid matrix, you open up a huge possibility. So this is the idea of all applications that use these magneto-viscous effects. So the idea is that you have nanoparticles, or in this case, you can have even microparticles, and they are tiny magnetic moments, as I mentioned, and they are isolated to each other. And whenever you apply a magnetic field, they turn to the magnetic field, and they can form chains, as you expect when you have beads of magnetic entities. So whenever you apply a magnetic field, they form chains, and these chains can change the viscosity of the system orders of magnitude. I don't have, I think, let me see if it's working. But okay, it's working. You see, this guy applies a magnetic field. It puts the magnet down, applies a magnetic field, and then, sorry. You can see that? So you can change the viscosity of the system by orders of magnitude. So these have interesting applications in for example, biofeedback knees or legs. This is a bridge in China when they applied this magnetorheological motion dampers. This was a region where there were strong winds, and depending on the cars here, they had a problem of stability of this bridge, and they installed this feedback controlled magnetorheological dampers in order to control the damping of the bridge. So there are many interesting applications that you can use, and of course you can use it in many different ideas. And if you can make a magnetic particle with some molecular cap, you can also think on biomedical applications. So, well, you can make environmental stuff, so you can control, and you can make, of course, rotating shafts, and you can make speakers, and anything that you need a control. And you need, for example, this is very interesting to the ones that works in vacuum. So you can make a ferrofluidic seal in order to make something rotating in a high vacuum, for example. The idea is to work now with these nanoparticles in health applications, and you have to remember that we are working in this regime where about below 10 nanometers, which is of the size of parts of DNA, viruses, and so on. The cells are around 10 to the 4th nanometers. So it's huge compared to the nanoparticles that we are using. And so we have many ideas on what to do with this kind of system. So just to mention, you can put a nanoparticle, a magnetic nanoparticle here with a biocompatible coating, a functionalization spacer, derivation, and so on. And you can install, put here at the end a drug, a protein, anything that you would like to make. And the first idea of any application is very simple. So you can, just to mention, you can make a very simple drug delivery. So if you have an inflammation, let's say you have an inflammation here. You put a magnet, and then you put in your blood a drug, a specific anti-inflammatory drug with low concentration. So you can put your magnet here. This drug will circulate in all your body, but you have a magnet here that will concentrate all the nanoparticles, magnetic nanoparticles, and you need to take less of that drug. You go to the place that you really need that. And so this is a very simple, straightforward application that you can already use. But some more, more interesting and more challenging application would be this one, which is called magnetohyperthermia. So the idea here is that the cells cannot live, of course, with a certain doses, but they cannot live above 45 degrees centigrade. So the idea is to connect this magnetic nanoparticle with a specific ligands in order to connect to a specific tumor or cancer or a specific tumor. So whenever you have that, you connect, you insert these nanoparticles in your body. This is interesting. These nanoparticles are made of iron oxide. And iron is you need iron. You can absorb iron in your body. Of course, in low doses, you can even have the iron without any problem. So it's biocompatible. And you can, whenever you connect these nanoparticles to the tumor, then you start a radio frequency field, magnetic field, and these nanoparticles start moving just as a, let's say, microwave. So they start moving in a tissue, and they just hit that place. They hit, and you can increase the temperature by 10, by 20 degrees without many problems. So you essentially what you do is you burn your tumor here. And of course, you have to remember this is nano. This is nano. It works very well with some metastases. So whenever you have very small tumors yet, it won't work with big-sized tumors. So you can see here examples. This is already in the market. So this is an example of a rat, you see, being treated by this magnetohyperthermia treatment. So a few minutes of essentially in a resonance machine, giving some magnetic field, and this can just turn out the tumor. So these are the kind of examples that people are already working on. And this is a huge, you can imagine that this is a huge industry that is growing. So there are already industries making these machines. They are already running some clinical trials in some different cancers. And this is a field which is moving forward very, very quickly. And so there are, of course, many challenges here. Just from the basic point of view is which kind of ligand, how you make this ligand work, and how, all the, it seems easier here, but it's, of course, much, much complex. Just to mention that this is very interesting and growing. And you can have other biomedical applications by control release of drugs, biochemical observations, and increase of contrast of magnetic resonance, and so on. So you can have a huge way of studying these nanomaterials. So this is a very interesting and very little explored field too. the biomagnetism. So just to mention, there are magnetotactic bacteria that they grow inside of them some nanoscopic iron oxides too, so they have this response to the magnetic field. Or you can have a lot of problems in biology which are not solved yet, such as social insects like ants or bees. They interact to each other, and apparently this interaction happens through nanomagnetism. Birds, turtles, reptiles. Just to mention one very well-known example is the pigeon, the homing pigeon. Nobody knows how it understands the magnetic fields and so on, and apparently they have regions of iron nanoparticles in the beak. So this is something that this is still to understand. So this is part of the collaborators, and I will stop here. Otherwise, I won't give time for any question or discussion. These are just examples of our lab, but I won't go through them. So thank you for your attention. Thank you very much. Yeah.
I'd like to invite the audience to ask questions to Professor Knobel.
So what was the problem you were mentioning about these dipole interactions that you skipped over it?
Okay. The main problem is that whenever you want to make, just to mention one application, which is magnetic recording that I mentioned in the beginning. So you have this tiny magnets which are close together, and you need to understand which is the role of the dipolar interactions, because the dipolar interactions change the anisotropy, and they change this magnetic response of the system, and of course you can change the stability of any device that you design. So it's important from the applications point of view to understand how the dipolar interactions affect the system itself. But of course, the dipolar interaction is a complex system by itself, and in my case, my particular question is how these dipolar interactions change the overall magnetic response of the system. And this is an open problem yet. There are groups of people which study or make Monte Carlo simulations or make a lot of stuff and say that the dipolar interactions go to one direction. Others claim that it goes to another direction, and nobody understands because it's an extremely complex many-body problem, which is still unsolved. So we worked trying to have a better understanding from the basics of this system, just that.
The concept of thermal jump that we were talking about, that was for an isolated nanoparticle, right?
Mm-hmm.
So if you have a pattern, a many-body system, right, and you just impose a kind of statistic from bits, right, on this many-particle system, right?
Yes.
You can, of course, change the relaxation time.
Exactly.
Right.
Yes.
So you can improve it significantly, right?
Yes.
Oh.
Yeah, you can improve, but on the other side, this is what exactly I was trying to just to mention one example. So you manage to develop a system which is isolated, is a magnetic nanoparticle, so you have an anisotropy, you have relaxation time, so on. But then you have this set of other, and they interact through dipolar interactions. And it's not only one or two, there are thousands and thousands, and these dipolar interactions can affect very strongly the behavior of. So the dipolar field in some way acts as an extra temperature for the system. Yeah. And then you can measure, indeed, what we do is exactly that. We associate the dipolar field to a fictitious temperature, and then we can measure that temperature, and then we can extract a lot of basic interaction parameters from these measurements. So from basic magnetic measurements, you can extract important parameters regarding interactions and how the system will develop and how it will behave. Exactly that.
So you had these amorphous nanoparticles in the matrix.
Yeah.
And what is the lifetime for those? Do they anneal away, or are they very stable?
Yes, they are very stable. They are not in a matrix. We managed to make them by chemical methods, so they are powder, and they are stable. But of course, if you make a thermal treatment, they crystallize. Yeah, you can make crystals and so on. But they are stable so far, and that's really interesting. But we don't know yet if they are really ferromagnetic from the beginning. So we are, from the basic point of view, there are so many new physics there. Nobody ever produced a nickel amorphous nanoparticle, and nobody knows if it's really ferromagnetic at certain temperature, or which is the temperature, or when it changed from ferromagnetic to paramagnetic. It's completely new field to explore yet.
Do you think that someday photonics memories can, emerge and overcome these problems? Because of course they are so, integrated, and they can have very smaller size, and the quality factor of microcavities that people are making in photonics these days is 10 power 6. So I guess sometime they would be better solution for recording information, right?
Yes, could be. There are many. I'm not aware exactly how it's going and how it's growing, but there are many alternatives indeed. The problem is that in industry, one parameter is the physical, response and so on. But there are others that we have to consider from the industry point of view. As you know, there is a huge industry down there already installed, and in order to make a new plant to produce thousands and millions of devices, this is something that you have to consider. Market problems, of course, the velocity, the price, and everything that you have to put together in order to see which will be the winner technology. And nobody understands very well yet how it will evolve. This is, I don't know. Nobody knows the answer yet.
Okay, thanks.
Thanks for the presentation. As you mentioned, drug delivery is a new and interesting application for magnetic particles. I have a question. Is there any side effects by using magnetic particles in the body in real application?
Yes. I'm not an expert, but I heard, at least from people who works more and more in this field. But for example, if you make some applications of iron oxide nanoparticles, up to a certain doses, no problem, because it's easily expelled by the body. If the body needs it, you can absorb that iron. You know that there are people that need. My mom, for example, she takes a pill of iron to compensate a problem of anemia that she has. So sometimes we have to take iron by ourselves. So, but I heard that it could be a problem. And of course, if you have a better product, they are now trying to make a specific alloys. So it's iron by itself is not good enough, so they are trying to put iron with manganese, and then that can have problems with some other element that can be dangerous. So they are working on that. But as far as I know, iron is the less dangerous to our body.
Because of time, we're going to stop the seminar and the questions here. I'd like to ask you to join me in thanking Professor
Okay,
Knobel.
thank you.